Hello students, welcome back. So in the lecture yesterday, we discussed in the previous video, we discussed reversible process, the concept of reversibility. Okay. Now I wish to link this concept with second law of thermodynamics. Please remember that I told you that in nature, no process is reversible. Okay. All the processes occurring in nature are irreversible. For example, heat transfer, which takes place from high temperature to low temperature body, is a irreversible process. Okay? Or any expansion of gas is a irreversible process. Reversible process is a imagined process. There is a logic in it, logic in the imagination, so it's not fantasy, but it's still imaginary process. And we saw that quasi-static process of expansion, compression, whatever, is one example of a reversible process. And heat transfer across infinitesimal temperature difference is also an example of reversible heat transfer, right? Reversible process. So today I just want to link this concept with the second law of thermodynamics. So let's imagine a process which is actually irreversible, which is occurring in nature, but we imagine it to be reversible. And if we make that assumption, not imagination, assumption, if we assume an actual irreversible process to be a reversible one, we can show that it amounts to violation of second law of thermodynamics, right? It amounts to violation of second law of thermodynamics. Now consider this process. Consider a box made up of two compartments. That means there is a partition here, right? So there are two compartments, and I am insulating this box. This entire box is insulated, meaning what? There is no heat transfer. Okay, and let's consider this is our system boundary. Okay, and we are assuming that in this compartment, let's say compartment A, there is gas and it has some pressure. Okay, whereas here there is vacuum. Okay, there is vacuum here. Now, so basically, please recollect, there is no heat transfer, there is no chance of any heat flowing to the gas inside here, or if the gas moves as we see here, we'll see later, there is no heat transfer across the system boundary, right? It's completely insulated. And this is high pressure gas. There is obviously zero pressure, it's vacuum here. I'll write this as vacuum here, this is vacuum. So now suppose we make a hole here, okay, we make a hole in the partition. You can logically say, intuitively say, not logically, rather intuitively say that the gas from here will rush to the other side, because this is vacuum, this is high pressure region. The gas would rush to the other side. So it is in a way expansion. The gas occupied this volume, now the gas will be occupied this entire volume, right? So this is a process which has taken place. Initial volume of gas was only this much. Now if you call this B partition, if you say volume A, VA is volume of this, VB is volume of second partition. Now after this hole is made, the gas would occupy the entire volume. That means its volume has increased. Now it will be VA, V suffix A plus V suffix B. Okay, so this is a process of expansion. Okay, this is a free expansion. Why it is a free expansion? Because there was no resistance to this expansion. It is vacuum, total vacuum. Okay, so now this process actually is a irreversible process, and you can see why. Because simple, because this process is caused by finite pressure difference. It's in quasi-static process, which is a reversible process, expansion always takes place because of imbalance force which is an infinitesimal. Remember the piston, infinite slices, removal of one slice. All that will tell you immediately that the quasi-static expansion is caused by infinitesimal inequilibrium force, whereas here it is a finite inequilibrium force, because there is this high pressure, zero pressure here, and expansion taking place. It's a free expansion. Okay. Now, if you assume, that means this process is irreversible, can be easily understood, because you can say that gas has moved from here to here spontaneously, so it will have new volume and maybe new pressure, lower pressure obviously because volume has increased. But now you cannot expect the gas from this side on its own, that means spontaneously, again going back here, and again you get all the gas inside in the first chamber or first compartment and vacuum here. That won't happen, right? The gas cannot move spontaneously back. So this process where the gas has expanded is an irreversible process. Now let's assume that this is a reversible process, right? Let's assume that, and then we can show that this amounts to violation of second law. Okay, so let's say that the gas has expanded. This is what, and the gas is going to come back. Gas is capable of organizing itself and getting back. Let's make that absurd looking assumption. Okay. Now say, let's begin from here. So now there is no hole, there is no hole in the compartment, but what is being done now is there are two openings made here, and these two openings are connected. Okay, these two openings are connected. As soon as there is connection established, it is as good as making a hole here. You can understand that. So what will happen? The gas will start flowing from here and would enter the other side. Isn't it obvious? It's obvious because there is no pressure here. The gas would move like this. But what is done here is there is a wheel, some mechanical wheel placed in the way, right? So there is a wheel which is placed in the way. So what happens? Because this is a high pressure gas, on the other side there is initially zero pressure. So what will happen? When the gas is running over this wheel will rotate. That means there will be some work. Some work will be available, right? And the gas enters here. Okay? The gas enters here. So during this process, we made some mechanical object to move, and as a result you got some work. Okay. Now, since our assumption is that, now once the gas has, so what will happen ultimately? Some portion of some gas will rush on the other side. The pressure on both the sides in both the compartments will be equal, right? And the gas flow would stop, right? Now what we do, we say that now we close this. We are closing this. Okay, we have closed this, and now our assumption is that this gas can on its own go back to initial compartment if there is opening. Okay, so we make an opening here. We make an opening and assume that, imagine, right, that all the gas from here, because we imagine reversible process. This expansion process we are imagining it to be reversible. So what will happen? It means all the gas will come back to this side. Okay, but before that I just missed one point. Okay, we can continue with this. So all the gas will come back here. I think I should just make a correction here. Before the gas comes back here, what we do, we know that the gas has given out certain energy. Why? Because there is work output, right? There is work output. So the energy content of the gas has decreased. By how much? By W. If W is 100 kilojoules, then the energy content of the, because you apply first law of thermodynamics, Q is equal to delta U plus W. There is no heat transfer, so Q is 0. So delta U plus W. So if you get W, that means it has to be at the expense of internal energy. So the internal energy of the gas must have dropped, and that drop must have been equal to 100 kilojoules. If you assume 100 kilojoules of work. So what you do, you imagine that you are transferring from the source. There is some source of heat, and from here you are transferring 100 kilojoules of heat. So you are transferring 100 kilojoules of heat. Remember, the gas is on both the sides. The gas has moved in this here, moved through the turbine wheel, one can say, or some wheel, and you have got work, and the gas is here. So gas is here as well as here, but it is at a lower, with a lower energy level. So now you are supplying heat. Okay, how much? It's exactly equal to 100 kilojoules. So gas now has same energy as it was, and now we expect that, we assume that all this gas spontaneously from compartment B moves to compartment A. Okay, it has moved to compartment A. So once it has moved to compartment A, we close this opening. We are closing this opening. Okay, let me clean this. Okay, so all the gas is here. All the gas is here. Once the gas is here, we remove this valve. Open these valves. What will happen? The gas will again flow over the turbine wheel, come back over here, right? Again you get 100 kilojoule. So you are getting continuously work output. As the gas comes here, we close these valves, supply heat, right? The gas, again open this, the gas will spontaneously come back here, close this, gas will flow, work will be obtained, right? So by assuming that the gas can organize itself spontaneously and go back to initial compartment, you are able to extract work continuously by taking heat from a single body. That means all the heat coming from the source, 100 kilojoules, is converted into work, and this cycle is completed, right? So this is a heat engine which is working in cycle and producing work by converting all the heat which it receives from a source. No need of sink. Source is giving the heat and it is converted into work. Now this is violation of second law, right? Kelvin-Planck statement. You remember Kelvin-Planck statement. This is violation of Kelvin-Planck statement. You are able to, if you assume the expansion of gas here, free expansion, to be reversible, that means you are making a claim that now you can have a heat engine which works in cycle and converts all the heat supplied to it into work, which is impossible, which is violation of second law. Thank you.